सर
हा बोला.
नाही काय नाही सर, मी चेक करत होती माझा लॉग्ड इन आहे की नाही म्हणून. बरोबर.
नाही नाही, तुम्ही लॉग इन आहात. यू आर लॉग इन. शैला मॅडम इज ट्राइंग टू लॉग इन.
ओके ओके सर.
She is having some issue. She will come back.
ओके सर. ओके.
Yes, madam. Madam, now can you unmute? Hello. Madam, unmute yourself.
हॅलो
मॅम हेडफोन
Yes, madam, I can hear you now.
हॅलो
हा मॅडम, आवाज येतोय.
हा ठीक आहे आता स्क्रीन शेअर करूया
हा आता एक काम करतो, आधी स्क्रीन शेअर करून टाकतो तुमची. आता स्नेहा मॅडम तुम्ही रिमूव्ह करा. मॅडम वॉज ट्राईंग व्हेरी हार्ड फ्रॉम लास्ट हाफ एन अवर. आय फोर्सिबली तुम्हाला कळत नाही. स्नेहा मॅडम
ओके मी माझा व्हिडिओ पण स्टार्ट करते 1-2 मिनिटं.
ओके सर.
व्हिडिओ मॅडम एक मिनिट थांबा. शैला मॅडम
ओके ओके
ओके. ठीक आहे, आम्ही ते आता इंट्रोड्यूस करूनच टाकू आता या स्क्रीनवरच, राहू द्या असं 2 मिनिट.
ओके.
मनीषा मॅडम गो अहेड.
your STTP design. It is a great pleasure for me to introduce our speaker for the today's afternoon session, Dr. Shaila Subbaraman, retired professor, Walton College of Engineering, Sangli. Dr. Shaila obtained her MTech from IIT Bangalore. She has done her PhD in radiation and hot carrier effects in submicron MOS devices from IIT Bombay in 1999. She served Walton College of Engineering, Sangli from 1989. She worked as a resource person for various workshops, autumn courses, guest lectures, expert lectures on MBA and OBE guidelines at various colleges in Maharashtra. She was deputed by NIU for delivering guidelines on NBA and OBE. She was working as an NBA NAC coordinator, head of department, and dean academics at Walton College of Engineering, Sangli. She had industry experience in various capacities: engineer, senior engineer, deputy manager for 14 years in semiconductor devices or IC manufacturing industries in Pune. Her areas of research interest are MOS design, digital system engineering, DSP VLSI, CMOS VLSI design, analog VLSI design, testing and testability. Welcome, ma'am. I request to join today's session.
Thank you, madam.
My pleasure, ma'am.
Yeah. So I would like to share the screen. Share.
Madam, access rights given to you. Yes.
Screen. The screen being shared? Hello?
Ma'am.
Yes, madam. Yes. Yes, madam. हो madam. Yes, yes. झालंय.
Okay,
या
ठीक.
फुल स्क्रीन मॅडम, फुल स्क्रीन करा.
Yeah. समझते.
Madam, your audio is also clear, madam.
Okay,
Shaila madam,
okay, sir.
your audio is also clear, video is also clear. Go ahead, ma'am.
Okay. Should I keep my video or should I?
Your choice. तुम्हाला
Sir, from your end.
थोडा वेळ.
Yeah, from your end, you try to, close my video. I'll only have the audio. Okay,
Achha.
I think continue. ठीक है. I'm very sorry for this late starting of my session. I am not on my table, my personal table at home. I am at somebody academy and are coming every time. But anyway, I think all of you know me, you will tolerate with me or for this delay of 10 to 15 minutes. So the topic given to me basically is VLSI implementation of signal processing algorithms. So when we say some information as a signal, and signal is a complex quantity. In the exponential form, we can write signal as equal to A into A e raised to z theta, whereas in the polar form, we write Z is equal to A cos theta plus J sin theta. It means it has a real component as cos theta and the imaginary component through sin theta. So when we are basically processing this information, which we call as the signal processing, we know number of transforms and their inverse and the convolution, correlation operations come into picture. And what is needed to is, as the information is received, we would like to process it. So it is basically real-time processing. We want to see a cricket match which is going in Australia at the same time when it is being played there. So what we need are the blocks which are processing this information. The hardware block should be fast, and most of these transforms and the other operations, DSP operations, involve the multiplication accumulation units. We'll see that. We know there are two methods. One is the Taylor series expansion, where we can go to solve this each term through software, or it could be iterative, where hardware and software, both approaches will come into picture. So in this connection, I will throw some light in my presentation, with special reference finally is a part 2 of this as a choroidic processor. Very interesting algorithm. It was actually invented way back in 1956, but with the VLSI technology flourishing or blooming, it has got an application. It's a very proper candidate for the VLSI implementation. So we'll see the various detailed signal processing architectures for the hardware implementation, and then we'll see that how a choroidic processor can be implemented with its nice algorithm. So the topic is VLSI signal processing with special reference to choroidic algorithm. I have organized part 1 basically will give you overview of DSP. I know all of you are very much aware of that. It just know, and basically the objectives of DSP and typical DSP processing. Then the various DSP architectures as such. Technology is useful for implementing these DSP architectures, and today's technology, I mean, which can be done sitting at home on your table itself, in your room using FPGAs. You do not need very expensive semiconductor manufacturing industry at your door, at your place to implement these DSP algorithms. And a nice choroidic processor with concept and implementation, that is the part 2. View of detailed signal processes. We know that it is a very, very mature technology as such on today. This has replaced the traditional analog signal processing system because of its advantages over analog systems, that is insensitivity to change in temperature. This is one thing, that is digital signals noise parameter is there. I mean, they can absorb a lot of noise. Insensitivity to aging, component tolerance, they can tolerate the plus minus 5% or 1% tolerance which will be there in the component. That is the beauty of even electronic designs. When we design our circuits, definitely the components are going to have some sort of tolerance, but it is being absorbed, and that is basically the designer has to see that the final functionality is obtained and it works in all the situations, in all the environmental conditions. Immunity to noise is one of the important things as far as signal processing is concerned. But we know that, I think this was also explained by me in the first part of STTP1, where because of the smaller size of the devices, or the smaller size, or the next technology parameter, now 5 nanometer we are talking about, and increase the component density. We are trying to pack millions of transistors in a small chip as such, and hence there is going to be a noise which has a concern with crosstalk noise. The two channels or the two conductors side by side will try to impress some sort of capacitive or the inductive noise there. There will be signal interference noise, return signal noise. So these are the things which one has to take care of that. But state-of-the-art technology which is there today can offer us a compact, a very small size area optimization, a low power. I think in the morning you had low power techniques I think I just had some opportunity to listen to the delivery as such. So you had some information regarding how we can get the low power VLSI designs, and also low cost. It has to become economical, and then only it will be popular as such. So the various DSP applications are in general purpose as filtering, convolution, various transforms. As far as speech processing is concerned, speech coding, decoding, encryption, decryption, speaker identification, echo cancellation. In audio processing, audio equalization, noise cancellation, all these things. In image or video processing, compression, decompression, image enhancement. In the information system, fax, modems, LAN, WAN, biomedical signal processing, controls, and instrumentation. That they find application. I think this is not new. I mean, all these applications, typical DSP system, I think this also was illustrated by one of the speakers in the STTP second perhaps, that we have a signal which is generally in the time domain, and we put anti-aliasing filter here. We have some sampling takes place here, goes through an ADC with analog signal, and the processing by digital, as we have said, becomes much easier, or I think that is the thing, is a trend as such, and hence we have to convert it into the digital DSP system, which basically will have the various transforms or the various processing computations comes into picture, giving either the digital output or converted back again into an analog, because in the real world we need analog in and analog out. So it is by the DAC converted into analog. So this is, I think, what we are going to consider. This delivery is on the DSP system, which will implement the various algorithms suitable for VLSI. So the objectives of any DSP system will be, you will maximize the performance by area optimization. So try to minimize the hardware circuitry. So obviously area get minimized. When you reduce the area or the number of components or the hardware circuitry, automatically the speed will be one of the reasons for that. One of the results is the speed also will increase. So this will give you higher throughput, can take up higher input, clock rate can be higher. Minimizing power dissipation again is one of the objectives. So energy required to perform any task. So we have to see that how low power can be obtained out of our algorithm or our architecture. Of course, low quantization and round off noise, some of the requirements of the DSPs for processing. The various computations here, as we have said, is convolution, correlation, digital filtering, adaptive filtering, motion estimation, the various transforms, Fourier, Laplace, Z transform, DCT, wavelet, and all. So if you look at the equations which are implemented in these operations, like convolution, if you take, you know that this is used to describe the LTI, that is linear time element systems. The equation as such, if you see, is that Xn is the input for this transform, giving In, which is Xn convolved with Hn is the unit impulse response. Hn is the unit impulse, unit sample response. So what we are doing here is that then when you try to consider a Yn for any Xn here, is a summation which for a k going from minus infinity to plus infinity, xk h of n minus k. I mean, this convolution operation now is expanded like this, where we see there is a multiplication of each sample with some parameter or the coefficient, and then you are going to sum it. This limit you can decide, or it can go from minus infinity to infinity, 0 to infinity, or you can stop depending upon how much accuracy you want. That k can be limited to 4 or 8 or whatever, or 20, 40, like that. So basically what I want to emphasize is this is nothing but a multiplication first, and then products are then added together. So the mag unit comes into picture here. Consider digital filters, which is the important class of LTI systems. Basically, these are designed to modify the frequency properties of the sequence of signal Xn to meet certain design requirements. These are characterized by either unit sample response Hn, or frequency response H e raised to j omega, or transform function or difference equation. Fire and IR, are the two important filters. Again, the equation, if you see, again is a summation of xk, a sample, kth sample, convolved with hn minus k, multiplication and then a summation. So MAC unit comes into picture. A correlation could be a autocorrelation or cross correlation. Again, the same thing. Try to write this detailed correlation operation in the matrix form, in the vector multiplication format. Then you can write it for n is equal to 4 in the matrix form like this. So these are the inner products. So array multiplication is there. Many times you come across this equation. The various transforms like Laplace, Z, Fourier, cosine. Integration will be in the analog domain, which goes when it goes into the discrete. Again, multiplication and summation, Z transform, which is a sequence into a complex frequency domain. You can have two-sided Z transform or unilateral Z transform. The limits will change. This is multiplication and Fourier transform, again integration, and hence you have multiplication with all these things. I mean, every see it's going to be a multiplication for the various samples with some coefficient and then adding those samples for k depending upon your requirement. And these are various transforms, complex. It through angle. Sometimes you will have to have the next and yes, transforms, just now we have said, are having the MAC as one of the very important operation in that. And all these things you need in the real time. So you would like to have it as fast as possible. So now how to map such data processing algorithms onto underlying hardware while meeting application constraints for power, performance, and area. We would like to have low power, high speed, and also it should consume as little. That's the optimum area. You cannot say as small as possible. It should be optimized. The optimization should be done for the power, performance, and area because there has to be a trade-off between these three. So to do these things, what DSP architecture designs and the VLSI technology are the keys for successful realization of many diverse applications in hardware. So you have the architectures, now we'll see that, and how VLSI technology is feeding that particular need of implementing these architectures successfully for meeting the constraints like power, area, and speed. So this basically is some sort of, I can say, introduction for the talk. Now this is the main thing. What are the various DSP architectures? We'll try to see those. Earlier designs, whatever hardware designs, were based on von Neumann architecture. It's nothing but the stored program architecture. And it will work sequentially. You know, take any processor, microprocessor or microcontroller, there will be a stored program concept and each and every instruction will be executed sequentially. Generally, it was not that high dense and hence power consumption was not serious issue at that time. However, the hardware was expensive and flexibility for implementing such designs was provided through software. You can write the programs to get any functionality being done by that process. If we consider today's design, then they are highly integrated. The complete system is on the chip and it is fully hardware approach. There will be thousands of multipliers and adders as the library components, or you can develop those. However, because of this, energy consumption has become a very, very critical issue. Because number of multipliers are there, the complete system is there, interfaces are there, you have to fetch the data from memory, again give the results to the memory, and all these things implemented in fully hardware approach is going to basically take a lot of energy. So this is a critical issue. performance is power constraint. I mean, that also you have seen. If you reduce the speed, power will be minimized. But then, I mean, if you reduce the clock rate, the power will be saved, but then it will become, I mean, the speed will be affected. Today's, I mean, designs, we have to again optimize, as we have said, for the performance and the power as such. However, additional benefit here is that when you were doing the earlier designs, which was basically the approach, ASIC approach, you were not getting the flexibility. That is, once the design is completely frozen with whatever, I mean, capability of that processor is there, you can write the programs and get working on that was not possible. But here you can have the reconfiguration, you can design the thing, implement it, and again try to say if it is not working, you can rework on that, redesign it, and reconfiguration aspect is there. So that flexibility has been provided today. So today's design are highly dense. Power, no doubt, is an issue. You have to consider that, but with not, I mean, technology getting to next scale, the VDD is decreasing, where I think dynamic power reduction is quite good. But then when the devices are close and they are having the source and drain very near to each other, the leakage powers are there, subthreshold leakage is there, low VTs are there. So these things need to be taken into consideration, and lot of research is going on how we can optimize on that. So these are some of the things which are giving us some sort of benefit to implement completely systems on the chip, but that on chip may be ASIC, okay, if at all the designs are fully and the requirement is large. But if at all you want to do it in your, I mean, wherever you are, without having any facility for implementation, you can do it using today's technology. So if we consider that what was there previously, now this is one example of 256 tap FIR filter. As we know that there is a multiplier and then the accumulation. So a multiplier as a hardware and the adder as an hardware has to be there. This could be an adder or subtractor depending upon what you are, whether you want to add or subtract. But then you will take the data, goes to the data will get multiplied with some constant or coefficient, then gets to the previous data, and like that you will have to do 256 cycles, that is 256 clock cycles to get the output. So unless that output is there, sample here, if at all for 256 step FIR filter you are implementing, you will not be able to basically, I mean, see the result of the next. That is, once a data is given to the register, it will go here, and such type of things, that is, you can say xn, xn minus 1, xn minus 2, will go all through these operations 256 times to give an output here, which will be yn. On the other hand, when you go for the FPGA implementation, where you will have 256 registers to store the data, that is, with every clock, if you are giving xn here, the previous will be present here, previous will be present here, because these are nothing but the storage elements. And then this data simultaneously will be available to these 256 multipliers, no doubt. Now one multiplier has gone. This adder also, though has been shown as one, there will be a pipelining approach here, that is, at a time for the adder we can add only 2 operand. So the result of that then makes the next operand, the result of this with the next, like that. There could be a pipelining again using some registers. But now it is possible for you in one clock cycle, finding out what is the critical time of this implementation, you can implement 256 step FIR filter. No doubt area, you will have to lose on area, and that is the trade-off we say. But using such type of the facility today through field programmable gate arrays, it is possible to have the FIR output, 256 step FIR filter output being outputted in one clock cycle instead of 256 clock cycles. And such FPGAs are available today, which can have 22 teramax of floating point performance, 7.3 teraflops of single precision floating, 11 teraflops of half precision floating point. So such a good facility, a tremendous computation facility is available with recent devices, and it's possible for us to develop these things in our college with the students and see the performance. And once, I mean, you can implement your own architectures So most popular architectures are the pipeline and the massive parallelism which is coming seen here. And as I have said, as far as this adder is concerned, there are going to be number of adders here, maybe 254, where with the storage of the intermediate result implement in one clock cycle, you will have the output of so pipeline and parallel, these are the two popular architectures as far as complete hardware approach is concerned. What is the pipelining architecture? Again, we have seen that when we consider a microprocessor, we know instruction fetch, decode, and execute. These are done in pipeline way. That is, when current instruction is being fetched, at that time the previous instruction is decoded and the previous instruction goes for the execution. So this acts as a pipeline. The pipeline will give some latency, but for streaming, when the data is getting streamed, you can tolerate that latency. After that latency, you will have the continuous output. So what is done in pipeline architecture is data is consumed, processed, and produced sequentially. Pipeline has a sequential operation. Of course, there is going to be intermediate storage. So pipelining is obtained by using generally D flip-flops are the obvious choice if LSI is concerned, not the other JK or T or the generally D flip-flops will be used. However, what we need to do is that one will be of moderate size in pipeline architecture. Adequate performance, you can try to decide how much speed and correspondingly try to put the storage elements in the combinational path, which we call as the critical path. So when you are implementing pipeline, either you can reduce the clock so that power gets reduced because it's always proportional to the clock frequency, or if you keep the same clock frequency, you can increase the throughput. So these are the pipelining and if you see pictorially here, let me say I want to implement yn is equal to an, bn, that is these are the coefficients. Xn is a sample. So an xn is basically has to be a multiplier. The addition has been shown here. Plus bn, yn is equal to an xn plus bn. So what you are trying to do here is that has to be a multiplier. I think I have put it. Is that okay? Or this is, yes, correct. This has to be multiplier. So now if at all you want to do it here without pipelining approach, you can say that the total time what it will take will have to take into consideration what is the execution time of these two hardware circuits, and hence you will not be able to really get this yn unless this execution is over. It means suppose the multiplier is taking 20 nanoseconds and this is taking, let me say 10 nanoseconds, then 30 nanoseconds, the samples can come only after 30 nanoseconds. That much time you will have to give. But if at all you try to put a delay element here, a storage element here, then you can store that multiplication and then can add this bn minus 1. I think some this will be n minus 1 into xn minus 1 plus bn minus 1. So what you get here output, if at all you put a delay element here, and if you have, this is a pipeline architecture because this combinational path, this multiplier is a combinational circuit, adder also is a combinational circuit. So if you try to break that, and this is going to limit the sample rate, the maximum clock frequency you will be working, or the sampling will be incident on this hardware as such as a unit. But if you put in that combination path a delay element, now it will be limited by the higher of the two. If this is taking, this multiplier is taking 20 nanoseconds, then definitely this will be limited by this, but it will be faster than the previous one. Of course, there is going to be a latency of, if it is 2 level, then after one cycle only, that is when xn is incident here, yn minus 1 will be outputted here. So this is latency one will have to tolerate, but that's what I said. If at all the data is coming sequentially one after the other at the rate which is decided by the execution time of higher execution time of the many hardware entities are there, then you can tolerate that latency. So this is a pipeline structure. Definitely you had to sacrifice on the area because the hardware is duplicated there. Process and produce in parallel. In the previous case, it was in pipeline. So there is no need of intermediate storage and operation scheduling. So because the hardware is a completely dedicated hardware is there, we have to only steer the samples. So obviously performance enhancement is going to be there, however, going to be expensive in terms of area. Let us see. Let me say the samples are coming and I time multiplex those samples. The even samples will go here to the upper branch, whereas the odd samples will go to the lower branch. Now the coefficients here are for this 8-2k. Since I am doing this two-level paralleling, I say this x2k and x2k plus 1. If at all I have n level, it will be xn plus 1, xn plus 2, like that. So I'll have to consider xnk plus 1, like that, where n will go from 0 to whatever infinity or whatever it is. The coefficients correspondingly will be, one of the operands of this will be the coefficients here, A2k, B2k, A2k plus 1, B2k plus 1. And now X2k is getting, I think again it is a multiplication. So this will take place. So even samples are going here. This operation is getting completed. But even before it goes to this adder or for the next execution, the next sample is going to be incident on this lower branch. And hence this gives fully whatever time is required to get correct output as Y2K and Y2K plus on these two branches, which are again time demultiplex and again are sent on a common channel. So what we have is that is a hardware duplication depending upon how many level parallel processing you want. Correspondingly, you steer the samples to the corresponding branch. When the outputs are there, again you demultiplex those and get the streaming of that. So this is the parallel processing operation. Here definitely the data rate will be done. Previously, if you do not apply it, you will have, let me say 100 megahertz is the clock rate. If you do it two-level parallel processing, you can work at even 200 megahertz at the data rate because each branch is getting full time for the execution of the hardware, and the samples will be multiplex and multiplex at the input, demultiplex at the output to get the correct output wherever you want. So either you can increase the speed or you can reduce the clock. Instead of 100 megahertz, you can work at 50 megahertz, the power conversion will take place. So one of the two, depending upon, you can do that. Now let me say another approach, which is a retiming. Retiming is something where you are trying to put the delay elements appropriately so that again it will work fast. These are, you can say, as high-speed architectures also. So let me consider again a 3-tap FIR filter with output Yn given as AXN plus BXN minus 1 plus CXN minus 2, and this is the DFD, data flow graph of that. Now let me say the multiplier delay here is of 20 nanoseconds and the adder delay of 10 nanoseconds. So at what rate we can input samples here? What will be the rate at which will be? What will be the clock frequency at which we'll have to give these samples to this hardware? Can anybody find out? Yes, you can unmute yourself and can tell me. If at all, I say that these are the samples XN, here's the delay element. So the previous sample will be here, available here, which acts as one of the operand of this multiplier, which is XN minus 2, XN minus 1. Again, there is a delay element. So simultaneously, Xn is incident here, Xn minus 1 is incident here, Xn minus 2 is incident here, which have been provided, these multiplier have been provided with a fixed coefficient as A, B, and C. And we are saying that this multiplier takes 20 nanoseconds for the execution of this one. These two operands are available there. And this adder, these are the two adders here to get this complete output Yn. And the adder delay is of 10 nanoseconds. What will be the maximum sample rate? Anybody? So what will be the maximum data arrival rate? These multipliers are going to work in parallel. So 20 nanoseconds, all the multipliers will give their output. Then this AXN is incident on this. BXN minus was as a operand for this adder. So this adder is going to take 10 nanoseconds. So 20 plus 10, 30 nanoseconds. And again, this result of output of this adder with this CXN minus 2, again 10 nanoseconds will be there. So to complete, once data is there, the minimum time required is 40 nanoseconds. And hence, the samples cannot come at a rate megahertz. So you'll have to have a clock where the samples will be inputted to this hardware, not at a frequency greater than 25 megahertz. This basically is limited because of what? Is not limited by these delay elements, but is limited by the combinational path. This multiplier, these two adder is a combinational path. And if many combinational paths are there from input to the output, what is the maximum combinational path delay? That basically is the critical path. So in this circuit, the critical path is of that 20 plus 10 plus 10, 40 nanoseconds. If we can reduce this critical path, it could be possible for to increase the frequency. Whether can we do that without affecting the input and output characteristics of the circuit? Is it possible for us to put some delay elements in that combinational path, which was a critical path, and this is the retiming, relocating the delay elements and increase the frequency? So let us try to see if at all we are saying this is the critical path and we put the delay elements in this path and in this path, what happens? So this is the original one. So what we have said is that Yn is equal to AXN plus BXN minus 1 plus CXN minus 2. Let us go to the Yn minus 1, the previous sample. It will be AXN minus 1, BXN minus 2, CXN minus 3. Previous. Yn minus 2, Axn minus 2, Bxn minus 3, Cxn minus 4. So these basically, each and every output sample is going to hold this type of relationship with the appropriate input samples X. Now let me say, as I said, I want to reduce the critical path delay, the path delay. So I tried to put in that combinational delay because I saw that this was the thing which was restricting the sample rate. So we put a delay element here and try to find out what will be Yn minus 2. Okay. Now you can see Xn is appearing here. So Axn, but delay element is here. So this will be Axn minus 1. When this is becoming Axn minus 1, at the same time this Xn with Xn minus 1, so this operand is Bxn minus 1, so Xn minus 1, Bxn minus 1. When it goes through delay element, this will be Axn minus 2 plus Bxn minus 2, and at that time these two delays also will have Xn minus 2, incident on this multiplier, and hence this will be Cxn minus 2. So what we are getting output here is Yn minus 2 as Axn minus 2 plus Bxn minus 2 plus Cxn minus 2. It means input and output characteristic of this three-type filter has been changed. So putting delay elements is not going to serve any purpose. This is not a correct way or the correct approach for putting this delay element. This reallocation is not good. So let us try to do now what we can do is that intelligently, let us try to say that when this sample Xn comes as an operand here with getting multiplied with that is Xn minus 2 having C as the coefficient. So Cxn minus 2, the maximum delay is that of 2Ds. So if at all I put 2D here after this multiplier, it is exactly the case like this, where this is Xn is going through 2D, but Xn minus 1 is with 1D and 2D going through 3D, and Xn minus 2 is 2D, that is this Xn is 2D and 2D 4D. That relationship of delaying has been done, latency is there, and now if we try to write equation for Yn minus 2, it is exactly same as this. So reallocation of the delay element in the combinational path, one will have to see how many and where is being done by the retiming approach. Now, this was a very, very simple example. We could do that even by the inspection, but in the complex DSP, circuits, it will not be that simple, and some algorithmic approach is a cut set retyping. Retiming, that you are saying that you are relocating registers. Now you have gone to 2 plus 2 plus 2, 6 Ds. They are increased in 2D. Now you have these 2Ds are there, but beside that 2 plus 2 plus 6 plus 2, 8Ds. Instead of 2Ds, now you have 8Ds. But obviously now it will be working at the rate of multiplier 20. So you can go to 50 megahertz. So this the increase in the speed, that is the performance enhancement is there. Or if you keep the same clock rate, then you will have less power. So these are some of the things that you have to minimize. Optimum number of registers, you can retiming can be done through algorithmic approaches are there. This itself will consume 1 or 2 hours. So I'm not going to the details. I'm giving exposure only to these type of techniques. Another, I think, DSP architecture is unfolding. Unfolding is like rope unlowering in software, and hence there is going to be the replicating of the hardware, which is similar to a parallel architecture. Another reverse of unfolding is a folding, where you are trying to do the work done by the reduced number of the functional units. So you are trying to reduce the functional units. However, there will be additional delays. So obviously, you are going to reduce the throughput as such. It will take longer delay because you are going to do the work of a DSP equation only by few instead of n number of units. So unfolding factor, folding factor, their algorithms come into picture. We know that in DSP, as I have said many times, we have to do the matrix multiplications in our products, and for that systolic array is the approach. See unfolding. I have taken one example that, as I have said, it is a loop like similar to loop unrolling in software. So let me say J is a factor. Then whatever you are doing in one clock cycle will be done in J consecutive iterations. So if I consider an example, let me say yn is equal to ay n minus 9 plus xn, and this is the DSP equation we want to implement. If you do not consider the unfolding or any other, you can see that xn, this yn, how this yn is coming? Yn is coming 9D as a delay here, a multiplier operand as a is getting multiplied. So this yn after a delay of getting multiplied by a, so this is a yn minus 9. So 9 getting added with the current sample, which is xn. So y of xn, and the same yn being delayed by 9 cycles multiplied by a. So this basically is sort of, I can say, data flow equation. Now, obviously, what you can say again here is multiplier, maybe as I said 20 nanoseconds. This adder takes 30 nanoseconds is the delay here. So you cannot, that is, this is a critical path. So you cannot have the samples coming at a period which is less than that. So we want to basically reduce it by approach which is called as the you can go to J, that is the factor is J. You can have 10 level unfolding. Here I consider a simple case of 2 unfolded version of 2 unfolded version. It means I will write the equation for y2k and y2 consecutive samples which are coming out of it, out of 2 consecutive 2k and x2k plus 1. So I just rewrite this. Again, this is by it's not possible for the complex DSP circuit. We'll have to use those algorithms. But at present, I'm just trying to give you an idea. So what I do is that this, if I write k is equal to ay, n is 2k here, 2k to 5 plus minus 10 plus 1 is it was n plus something 2k. in more plus 2k terms, you can come to picture when we consider if you see two unfolded version, there are two adders, two multipliers. But if you concentrate on what is my work, you can see here is that this Y2K is nothing but is coming here, is coming from this one A. So X2K going through a 5 clock cycle delay, getting multiplied by A. So A into 2K 5 times delay, and then getting added with X2K. So Y2K is X2K, but getting added with X2K plus 1 delayed by 5, then multiplied by A, and you are getting it Y2K, which is exactly same as this. Similarly, Y2K plus 1 is happening with, you can see here is that Y2K is coming here. So it is through a delay of a multiplier A with X2K going through 4D delay, getting multiplied by A, getting added with X2K plus to give you Y2K plus 1. So these equations are satisfied. It means instead of 9 delay, which has been splitted into 5D and 4D, this is the reallocation of the delay elements to give the same input-output function. Hardware has increased, but definitely now combinational delay has reduced. So the number of delay elements, the total number of delay elements will be the same, but they have been relocated like this. So this is similar to parallel processing, duplicating the functional blocks to increase the throughput. The throughput will be at a higher rate, and we can implement the word parallel or bit parallel architecture. It is just the reverse of this. It means you are trying to minimize the number of functional blocks in synthesizing DSP architecture. Whatever you do in unit time, you will require 8 unit times. Exactly reverse of that. So though it reduces number of functional units, obviously it will increase memory units because you will have to have the storage of the intermediate results, and this will reduce the throughput also. Again, later you basically want to have yn is equal to an plus bn plus cn. So these are just the addition of 3 numbers. Obviously, when on paper also, when we do that, we'll add these 2 numbers first, then to the result, we'll add this and get the output. Similar has been done through an hardware here. So you have this first adder with an and bn as the operands. The result of this after completion of execution of this will be available here, which is the one of the operands of this with cn and yn here. Now the total combinational path here is the 2 adders. So 10 plus 10, if I consider 20 nanoseconds, will be the minimum sample rate, that is the sample period. After that only the new sample can come here, otherwise the corruption will take place. Now whether it is possible for me, there are 2 adder units, whether it is possible for me to implement these same equation using only 1 adder, this is the question. So yes, let us try to do that. What we were doing is that add these 2 first. So initially you consider for 1 adder, these are the 2 operands. And the result of that needs to be stored. It means there is going to be some delay element here. And the result of that again has to be one of the operands of this. It means it should be diverted here to the one of the operands. Instead of an, it will be the result of a and bn. And that time instead of bn, cn will be there. So you have to basically implement some sort of switching here. You have to have the switching of the corresponding operands at the appropriate time. And when this goes in the first cycle where an and bn were, or you can say even samples, at that time yn will be the output. So let us try to see that. This is only 1 adder. Instead of 2 adders, there is 1 adder and delay element. So storage element is there. Now, there is a switching at 3 places. At the input one of the operands of this, the other operand of this, and the third is for the result. So that the switches and how this switching is taking place. Let me consider this is L is an iteration. What is that iteration? Let us consider L is 0 initially. So what we have got here is that A0 and B0. To L plus 0, this switch will be on this side. It means one of the operand will be B0. The other operand is A0. This will be added. Here is A0, B0. Now this is stored. When the next clock comes, then only it will go here as A0, B0. And then is available here. When the next clock comes, this switch is going to come on this side, where this switch will have connection to this CN, and hence whatever will be added is the previous stored result of A0, B0 with CN, and with the next clock, that is when the third clock comes, that time you will have A1, B1 available here, but the result will be going here as Y0. So you can see here, if you consider the 0th cycle, the adder input left will be A0, B0, and hence in the first cycle, A0, B0 will be the adder in adder C0 will be the input here, but the system will not be there because the switch is on. This switch will be only for the even odd cycles. So when the next even cycle comes, that time it will be outputted. So there is going cycle latency here. You will get the result only after 2, but the hardware is reduced and complete power also may get reduced. However, throughput is reduced, area optimization. This is a folding effort. This switching again, how to switch these foreign complex again is a very tedious algorithm. We'll have to see what what is the folding factor as such, what is the complexity of this, what are the, there could be number of combinational units, all need to be replicated, and the switching is to be intelligently done. But this is not by inspection. Again, one will have to implement the algorithm. So throughput is reduced. Area. Systolic arrays, I think you know, it's many times inner products are there, and is one of the efficient array architecture. So why the name systolic is like a blood flow in our heart. So these are the processing elements. All are exactly same. They will take the data, process the data, and give to the next processing element in a rhythmic order, done very systematically. So it is like taking data in and out and sequentially, and generally applied when you want to have some sort of co-processor thing in along with the host processor. For example, let me say you have some floating point operation, which is fmul is the instruction there, and then which will be done by the co-processor, because host processor will be doing some other thing there, busy doing some other thing. So it will give it to the co-processors. It will go through this. So there I think we can implement this type of system, which is the systolic array system. We'll do that, and the data out will be given to the host processor. So considering this, I said that regularity and modularity are the features of these systolic arrays, and use point computation or the co-processors, and data samples received from host processor pass through processing elements. The result is again returned to the processor. Generally, you have learned, as a DSP, you have learned DSP, you know that DFG, SFG, DG, these are the various graphical methods of representing the DSP equation. So this basically is called as the dependence graph. So this is DG representation again of a 3-tap FIR filter with the equation Y, these are the weights, W0, W1, W2, this is Xn, Xn minus 1, Xn minus 2. So if you see here, these X samples are advertised along this Y-axis. So X0 at 0, X1 is space representation, X2 at 2, and so on. And along the Y-axis, we have, so along the X-axis, we have W0, W1, W2 as this one coefficients, you can say. So now you can just try to see what this Y3 is or Y2 is. Let me say it is a 3-tap filter. So what this Y2 is. These are the nodes which are the processing elements. These are the MAC units as such. There are the 3 edges. One edge is coming like this, which is nothing, your sample edge. The other edge is for all the processing elements is this weight edge. And the third edge is the result edge. Is going for each the processing element, we have the 3 edges. Let us concentrate on Y2, how Y2 is there. It's coming from here. What is this? This is a MAC unit. Initially, it will be 0. Or what it does is that this X0 is multiplied with W2. So you have X0 getting multiplied with W2. This is given to the next processing element where you have this X1 getting multiplied with W1, so W1 X1, the addition takes place here. So you have W2 X0, W1 X1 plus W1 X1, come this result coming here, and here you have X2 sample coming with getting multiplied with W0, and you have Y2 is given by this. So the outputs will go on coming sequentially like this. Now this is the space representation of data graph. In systolic arrays, we have to consider time factor also, and hence space. And for that, there are some sort of transformation converting a space array into the space time. Again, I am not going to detail of that, but vector and the scheduling vector. The same processor vector will come into picture number of times, which is decided by the scheduling vector. And for that systolic array deciding the processor vector and the scheduling vector with some restrictions come into picture. So these are the various things, whatever we have said that the DSP computations needed to be done through various DSP architectures, which are VLSI implementable, can be done using various pipelining, parallel processing, folding, unfolding, or retiming, systolic arrays. So these are the various DSP for VLSI implementation. So I think I can take some 5 minutes break here. If you have any doubt, this was my part 1 where I had taken the overview of the DSP. What are the requirements of that? What are the various DSP computations and the DSP architectures? If you have any sort of query here, you can ask me, and then we can go for the VLSI implementation, and then the example of a Cordic processor. So any participants, any doubt, you can unmute yourself.
Anyone wants to ask anything?
Hello? Okay, then I think I'll go to the part 2, which is VLSI technology for implementation of the.
Yes, madam, go ahead.
Okay. That if at all we had to implement it at the transistor level, and using, these architectures implemented physically, maybe in today's technologies, 18 nanometer or 5 nanometer, which definitely is going to have optimizations as speed is concerned, power is concerned, area is concerned. The customer specification, your designer will give the architecture level, will have the RTL of that, then version of that, and then we'll go to the physical layout level also, and we'll implement that. We'll have to take into consideration the issues of signal integrity, noise because of the placement of the components, maybe the components developed by the designer or the library components. However, this ASIC development is going to have a huge capital investment and the recurring cost also. And it's justified only when you are fully sure that your design is going to work. The requirement is large and recurring. Otherwise, what we can do is using the programmable logic devices technology. Now the PLD Plaza CPLDs also can implement for learning. As far as implementation of the complex DSP computations or DSP circuits are concerned, or even other, we would like to use some programmable DSPs, like you might have learned about TMS320, which is based on this architecture. You have these are the DSP algorithms which are MAC intensive, and hence there will be some library components or the IPs of array multipliers, fast array multipliers. You can have the word width of going from 8 to 32 at present in TMS320. You can the recent ones also, which can go to 64-bit also. You can use multi-stage pipeline structure, programmable DSPs, and can achieve higher MAC rates. So this is what currently happens. You can have completely dedicated FPGA technology where number of resources there, you can fully it and try to implement using the tools like Xilinx, Altera, Atmel, only the functional simulation. It will synthesize whatever components are there and try to give you the idea about the delays or the maximum frequency it can work. After place and route of those components and giving programmable interconnects, again you can see what are the delays after PAR, and then you can implement simulation wise in a particular FPGA of your choice, and then see that whatever functionality you wanted, even in the adverse condition, it is working. So this is the FP technology. Basically, it's a very handy technology. With advanced tools like this, you can make your designs to work. So FPGAs basically is an intermediate, we can say, a processor, a general purpose processor, and a fully custom ASICs which is implemented at the transistor level. They have reconfigurable architecture. They come that we can have in-circuit programmability, reprogrammable and reconfigurability is the aspect associated with FPGAs. We can design full microprocessor or full microcontroller can act as an IP, and you can basically implement that and then have the associated circuitry, connect the input output devices, and you can completely have system on FPGAs of your design, which perhaps if not working, you can again rework on that and make it work. They generally will have lower clock speeds, but a massive, what we have said, inherent parallelism is a speciality of the FPGAs, and hence they will work faster even than the general purpose processor. So perhaps they have a lower clock speed, and that is good so that your dynamic power dissipated will be reduced. But the throughput will be there because it gets implemented at the hardware level. They provide high performance solution for many applications and low power also. Economical solution with time to market. This is one of the things that after design and development, how fast you can bring your product into the market. So it's a very, very economical solution. You don't have to really worry about the capital intensive facility with you. It is generally tailor-made, however, for low volume requirement and only the prototype development. You may give it, if the requirement of few hundreds also, you can give it to the industries by developing the things in FPGAs, but if the requirement is going to be in millions, like our mobile chips and all that, definitely ASIC, that is at the silicon level, will have to do the work. So DSP features of FPGAs are generally adders are there. It means the algorithm which will be implemented there has to be a fast one. So fast carry logic instead of look ahead adders. Generally, we learn about the look ahead adder. It will be a faster, keep the things ready. But the fast carry logic is implemented in FPGAs, which is a built-in feature of FPGAs. Then number of library components will be available, which we call as the IPs. Array multiplier will be there, adders, DSP cores will be there. Then embedded hardware microprocessors or microcontrollers like Spartan 6, Vertex, Excalibur, PowerPC. I mean, these are the FPGAs, and these are the processors or the controllers available for you, which can be used as IP. You don't have to develop those, and use this as a library component. There will be the external memory support as such besides online memory. Ultra high serial interfaces will be there, and tri-state programmable slew rate, read back or boundary scan decoder. So these are the features of that required for the DSP or even normal implementation of the combinational or the sequential logic. So as we have seen, it will exploit the inherent parallelism in the algorithm. They will try to see which things can be done in parallel, and correspondingly the hardware will be placed there. Is based on the application. Any type of arithmetic like integer, fixed point, floating point can be implemented. FPGA design technology creates designs automatically to match the program specification even without much knowledge of the designer regarding circuits. That is, if he knows a higher level, that is VHDL or Verilog type, and he knows the logical sequence of that without going into much details which happens at the back end or at the transistor level, he also can design those. The FPGAs are reusable, reprogrammable, as we have said. Faster prototyping is there. Non-recurring cost is very low. And there are the FPGAs of varying device capacity in terms of logic blocks, performance, routing resources, memory, etc. And that is why I think we can definitely work with our students using FPGAs for implementing circuits which could be of DSP or others also. Now with this, now let us architecture or the of a Cordic processor, which is one of the proper ADC implementation, which is this does number of jobs which are computations. Generally in the handheld calculator will have this Cordic processor, which are generally the transcendental functions. So Cordic is a coordinate rotation digital computer. It's an iterative algorithm for the rotation of student. The basic thing is that we consider the rotation of a two-dimensional vector there in the linear, circular, or hyperbolic coordinate system. And scientific computations are done not using multipliers. It's a multiplier-less multiplication is done in the Cordic, which is again the speciality of this algorithm. There are only adder, which is correspondingly economical operation, and the shift using barrel shifters. You can shift the decimal point to the left or right. So, as we have said, used for trigonometric functions like sine, cos, tan, cot, hyperbolic, logarithmic, exponentials. We generally are computed numerically using Taylor series expansion. Mostly, I think we'll try to see how sin x and cos x can be obtained by using this algorithm, what is the basis of that. And once we have sin x and cos x for the angles between 0 at the first quadrant, 0 to 90, any other trigonometric function can be derived from this. This will compute trigonometric functions much faster than basically implementing Taylor series in the hardware, and is preferred choice for the low-level hardware, generally used on a hand calculator, and gives a very good accuracy that we try to. There are two factors which are responsible for fast Cordic algorithm. We know that if we consider a binary number and multiply it by 2 raised to n, then what we have to do is that shift the binary point n places to the right. And when we divide by 2 raised to n, we shift the binary point n places to the left. Example, this is 1011.11, a floating point number, a binary number I have considered. The binary point is here. Its value is 11.75 in the decimal. I shift the binary point by one place. What I get is this. What is this value? Is 23 point decimal, is exactly double of that. So shifting a binary point by one place to the right has multiplied this number by 2. If I do it by n places, then it will multiply by n places. Similarly, if I consider this as a number and take binary point left by one position to the left, the number gets divided by 2. So this is the basic beauty of our binary numbers, and shifting in the powers of 2 will basically multiply by that power of 2 or divide by 2. So coming is computers that are economical and fastest to perform or addition subtraction, comparison of two numbers using relational operators less than, greater than, equal to, not equal to, storing and retrieving numbers from the memory, only it is a fetch date operation, and shifting the binary point is shifting, either is a wired shifting or it could be the barrel shifter like thing coming into picture, but no multiplication division is coming into picture because they are costly and take time. So these operations can be done faster, and Cordic exactly uses all these A to D operations in implementing its algorithm. So let me say, coming to the basic of that Cordic, a vector rotation, analytical treatment. Let me say initially my vector in the coordinate two-dimensional Cartesian coordinate system is like this, x in and y in, with this x in and y are the coordinates starting from the origin. The one point is at the origin, the other is here, having beta as the angle with x-axis. And I rotate it through angle theta further with a final position, a rotated position as xr and yr. Let me say mn is the length of this, which is modulus of the vector, and beta initial angle, theta is the rotational angle. So using simple thing, I can write xr and yr in terms of x in and y in using simple. We know if I just consider What is XR is nothing but M in cos of beta plus theta. And what is YR? YR is nothing but M in sine of beta plus theta. And now if you use and all that, you can write finally that this Mn cos beta is nothing but your x in, and Mn sin beta is nothing but y in. This should be in initial vector, and hence in the matrix format I can write xr and yr as is a rotational vector rotating through theta, cos theta minus sin theta cos theta, x in y in. So this is in the matrix form. I had tried to write the coordinates of an rotated vector xr and yr in terms of the initial vectors x in, y in, and using this matrix in the matrix form, a theta is rotated through theta and sine and cos. So what I need to do is that I have to find out the cos and sine values of this theta to find out the final xr and yr with combined with x in. Now I am not going to do it. I will not take directly through theta. I will try to decompose that theta into the small angles, which are the micro rotations. So I will have alpha j as a micro rotation going from j equal to 0 to theta. Finally, if I accumulate those angles, it will be theta. And if I consider that, then my this operator rho theta becomes product of rotations of alpha j, what are the small micro rotations we are going to take so as to get that final angle theta through the summation of this will be given by this will be a product, because you have the product rho theta into x in y in, and hence it becomes. How alpha j is to be chosen, that is another thing. This alpha j should be chosen such that, and this will be hardwired in the computer, which are the tangents. Tangents are of the form of 1 upon 2 raised to n. That is, tan theta will be 1 upon 2 raised to n, where n will go from 0 to whatever number of iterations you would like to do it. Initially, n will be 0, it means it will be 1. So tan theta is 1, so the angle will be 45. Next time, it will be half, so tan theta is 0.5, so theta will be some 22.7, like that. So this is a case, that is alpha j values, that is these micro rotations will be chosen in such a way that is their tan thetas are the powers of 2, 1 upon 2 raised to the negative powers of 2 with n going from this. And you can see as you go on doing this, tan theta will become 1, half, 0.5, 0.25, 0.125, 0.0625, and definitely the angle will become tan theta, that is the angle will become smaller and smaller, and finally you come to a location, position such that tan theta itself is theta. We know when theta is small, sin theta is equal to theta, cos theta is 0, so tan theta will be almost equal to theta. So the values whatever you have to store will not be of tan theta, will be of theta itself. So this is the beauty of this. And hence in that case, again, if we concentrate on what is, if I consider alpha j as the rotation from some position j to j plus 1 iteratively when I am going, so xrj plus 1 depends upon xrj and yrj through that cos alpha j and sin alpha j given by this equation. The same thing, previously it was x final, y final in terms of x in. Now I am going to that theta rotation through small micro rotations, and hence in the iteration j plus 1 first iteration and the coordinate values xr and yr of that rotated vector in terms of this will be written by this equation. Now what I am going will take cos alpha j as a common factor here, and hence this will be xrj and this will be sin alpha j upon cos alpha j, so tan alpha j. So what we had tried to do is that some common factor we had taken out of these two terms. Now what we see here is that there is a multiplication 1, 2, 3, 4 and 2 adders. So there are the 4 multiplications and the 2 adders, and we already have said that alpha j is some specific angle we are going to choose. Come into picture for these 2 equations for implementation will be, let us concentrate on one. What is this xrj plus 1? Xrj plus 1 is the next iterated x coordinate of that particular rotational vector. It is getting multiplied by cos alpha j. So cos alpha j is there. After what? After adding or subtracting, adder acts as a subtractor also, xrj. So XRJ is coming from here, and the other one is YRJ and tan alpha j. So you have this particular sort of thing we'll have to implement if we have to implement these equations as they are. It means there are 1, 2, 3, 4 multipliers and 2 adders. Whether still further it can be reduced, and we are saying that we are going to do multiplier-less multiplication there. Then what we are going to do? So what we are going to do further is that we'll consider that constant factor which is coming out. That constant factor was cos alpha j. And hence, when I go to the next modulus, that is that constant for the j plus first iteration from mj, it is 1 upon cos alpha j. mj. Cos alpha j was here. Alpha j. So the modulus of this will be in terms of this 1 upon cos alpha j of 1 upon cos alpha j of this mj. Now cos alpha j is written as sec alpha j, which is again under root 1 plus tan square alpha j, where alpha j again is tan alpha j is 2 raised to minus j. But this rotation can either be in the clockwise or anti-clockwise direction. So we are associating it with some sign factor sigma j, and hence this mj plus 1 becomes 1 plus 2 raised to minus 2j under root of this into mj. So we are trying to now get the next constant outside this in terms of the previous constant here which was there, or the coefficient or the term which was here, which is multiplied by this term, because tan alpha j is sigma j 2 raised to minus j, sigma j is plus or minus j, and we have that is mj plus 1 is 1 upon cos alpha j is expressed in terms of like this, and hence if we do this, all the operations for combining for accumulating theta for j is equal to 0 to infinity, then it is going to be a product of 1 plus 2 raised to minus 2j under root of this, and if we do this calculation, it will converge to this factor 1.6468. So now this term, that is from the initial to the final, when we are going through the micro rotation, the term which is going to be outside this is a constant term which is not dependent upon theta or the initial values of x in or y in, but it is a constant. So we know if this is a constant, perhaps we can bring this into the picture only in the last moment, eliminate this factor, and then have the equations, chordal equations as xj plus 1 is equal to xj minus sigma j 2 raised to minus j yj, or yj plus 1 is equal to like this. Now what is here? Now this is 2 raised to minus j yj is shifting by j positions to the depending upon whether it is plus or minus, either in the anti-clockwise or clockwise direction, similar like this, and an adder. So only an adder and a shift operation is coming into picture here for getting us a very complicated, or you can say the position of the rotated vector in terms of its rotated coordinates xr and yr. So this way we have tried to eliminate this. I was talking about what is stored in the computer is the tan inverse of 2 raised to 0, 2 raised to 1, 2 raised to 2, and so on. And if you see, as theta goes on basically decreasing, that is when it is tan inverse of theta 4 is equal to tan inverse of 1 by 16, which is 0.0625, you see that pi by 4, that theta itself is 0.0624. So initially, from 45 degree, you had this is what I want to say is that this theta was 1, but this was 0.78 in terms of radians. There was a large gap here. This goes on decreasing. Half is 0.5, which was coming 0.46. This is 0.25, very near to 0.25. This is 0.125, again 0.124355, very near to this. So if you go on doing it for large iterations of those alpha j, you see that tan theta is nothing but the theta, and hence you did not store all values, only theta can be stored there, because slowly when it converges, the theta becomes very small. This as an example. Let me take that x in y initially is here, and I want to rotate it through angle theta, taking the final position at xf and yf. So initially when we are rotating for this will be tan inverse of 1, which is a 45 degree. So from here, the vector gets rotated here by 45 degree, it comes here. So this is my x1, y1. No doubt in the picture, this modulus has increased, but I think we consider that factor we'll consider later on, because at present that 1.6468 factor I haven't taken into consideration. So perhaps that is coming into picture here. Now, I know that my theta was here, but the rotated vector has gone here. It means I have to basically do it in the reverse direction. So my sign will be, instead of going in this anti-clockwise, it will be the clockwise. So what is the next angle? Tan inverse of half, which could be some 22. So from 45, this vector will be rotated here to the position x2, y2. And then I see now with respect to the initial position, it will be 45 minus that 22, whatever angle is there. So that is now accumulated angle is 23. Is 23 is greater than or less than whatever I want is less than. So take the next rotation in the anti-clockwise. It will be tan inverse of 1 by 4. It goes to x3, y3. Now the accumulated angle is greater than what angle I wanted. So again it gets in the clockwise direction. So this doing this type of oscillations, depending upon whether the accumulated angle is greater than the targeted angle or less, you are going to rotate it through tan inverse of 1 by 2 raised to z. And every time this angle you can see goes on decreasing, finally will converge to the value you want. And in that case, if you take the projection of that final vector on the x-axis, it will be cos theta, and the projection of that vector on the y-axis, it will be the sin theta. So this is by rotation. So systematically doing this rotation, you can get the final values which can be in terms of the cos theta and 90. Now, at present, we have seen that we have talked about xj plus 1 and yj plus 1. Now, we are trying another variable, which is the z variable. And this we call as the part of the angle rotated yet. So, we wanted to reach to theta, but by accumulating these micro rotations, I have come to a factor which is not rotated so as to get that value of theta. It means my rotations procedure will stop when these accumulated micro rotations will have the value of theta. So z is the part of that angle which has not been rotated, and hence when this term becomes negative, it means I have rotated through that accumulated angle is greater than the targeted angle. So you have anti-clockwise rotation. And if this is positive, it means so far the accumulated angle is less than, so you will go in the anti-clockwise direction. So this direction of the rotation, which is given by the sigma j factor, will be decided by the sign of this, where xj1 plus is positive, then is rotate it in the anti-clockwise so as to increase. If it is negative, then rotate in the clockwise direction so that the angle will get reduced. So this is one thing which is coming into picture now, which direction for that. And if you try to really find out what is that xj plus 1 in terms of xj, the iterative, it will come out to be, I mean, you can again go through this, I'll keep the PPTs, sigma j tan inverse of 2 raised to minus z. So here also the iterative third equation is coming into picture, which will give us by through which angle we'll have to rotate the further vector and in which direction. So now we have got the equations which are the chordic equations as xj plus iterative equation, xj plus 1 in terms of xj, yj, the rotation with sign, and this is nothing but the displacement in terms of or implementation, shifting of the binary point, yj plus 1 in terms of yj and xj, and zj plus 1, that is the part of the angle which is not rotated yet, is the remainder of that is given by this. So implementation of this in the hardware is the implementation of the chordic algorithm. So chordic is used in two modes. One is the rotation mode and the other one is the chordic mode, vectoring mode. And in the three coordinate systems is a circular coordinate system, which we were talking just now, hyperbolic coordinate system giving cos, sine, like that, hyperbolic trigonometric functions, or linear coordinate system. And depending upon the mode and the coordinate system you are implementing, you will have the various functions, the final function. So let us consider, I'm not going through all the details. This is exposure I'm trying to give to you. You can go through lot many papers are there or the literature is available there. I'm just trying to just create an interest in minds of you that this Cordic processor can do number of scientific operations very easily, that is fast and in very, I can say, finite number of iterations. So now this algorithm, what is rotation mode, is generally called as driving Z to 0. You are trying to make that that is the Z, what we have said, equal to 0. It means after accumulation all these micro rotations, you are coming to an angle theta. So theta minus summation of ZZ now becomes equal to 0. So this is driving Z to 0. The Cordic core computers these values. Now I know again bringing that k into picture, because we have come to a final case where that k 1.6468 needs to be taken into consideration, and you will say again a multiplier is required. Then what is the use of this Cordic processor? We'll see that in a time. So considering k, again I am trying to write the equation for xj plus 1 yj plus 1 only for x and y coordinate. Z doesn't have any factor here. So if we, let me start with initial values, as x0 is equal to x in is equal to 1 and y0 is equal to y in is equal to 0. So initially I am keeping y. It means I am keeping y vector on the x axis, and then we are rotating it, and then rotating so that my Z0 initially is theta, which is the targeted thing, and with the iterations, we'll try to bring this value theta to 0, and then what we are going to get, we'll try to see. So this is the initial value. So Zj plus 1 is Zj minus sigma j tan inverse of 2 raised to minus j with sigma j restriction. So now if I do that, what I have said is that initial theta, okay, so that is, I'm keeping that. Let me go back. Z0 is theta, Y0 is 0. So if Y0, consider Y0 is 0, then what you x in into cos theta. So cos theta is equal to, except because x has 1. So cos theta is equal to except by k. K is 1.6. Whatever final value of x coordinate you are getting for that rotated vector equal to 0 divided by k, you get cos theta. Then is equal to 1.6468. Why should we keep it 1? Let us keep it 1.6. Initially, when you are taking vector x in on the x-axis, instead of x in equal to 1, which was considered previously, if you keep it equal to k value itself, then here, since this is 0, you are considering that is only cos theta term will come into picture here. So you have getting multiplied and divided by k. So the equation it will be y0 is equal to y and equal to 0, z0 is equal to theta, and cos theta is equal to, except you are final getting the convergence and making that z equal to 0, finally making driving z equal to 0, starting with z equal to theta, you are slowly rotating from theta towards making z equal to 0. So whatever is the x, that is on the cos theta is nothing but except, and sin theta is the because k again gets multiply k sin theta is if you are again multiplying it by k, that is you are trying to mathematically eliminate this k by considering k is equal to 1.6468. So your final values of xf and yf after number of rotations will give you the value of cos theta, sin theta, and then possible for you to get all other trigonometric functions. Of course, the final xf is 0 because this is driving z to 0. So final xf will be 0, but then you get cos theta. Let me take an example. Let us say we want to convert this to 40, that is an angle of 40. So now you can see here at this position, that is we are considering, we'll take it on x equal to 1.6468. y is 0 and theta is where you have considered is equal to some value of theta, it is 40. That is, z is being fed with 40. The first angle you go to 45 because tan inverse of 1, so 45. Now 45 is greater than 40. So you do that comparison and your sign becomes minus. It means you have to rotate it in the reverse direction. So now second value of alpha is tan inverse of 0.5, which is the angle is 26.55. So initially you had gone to 45, but now in the reverse direction 26.55. So sigma alpha I will be 18.45. Now it is less than 40. So you have the positive direction for the rotation. Now you rotate it, but the angle will be tan inverse of 0.25, which is 14 degrees. Now you accumulate it. So 18.45 plus 14.03 will give you 32.48, less than this. So again positive rotation. Next angle is 7, 39.60, again positive. So next angle is 3.57, and like that you go on doing it. After 14 rotation, iterations, you go to a value of 40.003. You can still go further if you want, still more accuracy, but you are converging to a value which you wanted, and with initial value of x in as 1.6468. To eliminate that multiplication, final multiplication, whatever xf you will get after that getting 40 is a cos theta, and yf what you get will be the sin theta. So this is how. Another mode I have said, vectoring mode. The chordic equations are the same. However, the sequence is different here. Instead of bringing z to 0, you will force y to become 0. And then what you get will not be cos theta, sin theta, different. So again, I will come to that, what you get. Just excuse me for 1 minute. So let us say in the, depending upon the mode and system you are considering, the final outputs will be different. If you go for the rotation mode and the way I have explained, it will be getting the trigonometric functions. You go for the vectoring mode, it could be different. If your linear system is there, the outputs will be perhaps square root or logarithmic, something like that. That table will come to know. But here, hardware which goes into picture, irrespective of it is rotation or vectoring mode, it will be the same, implementing the same equations, because the equations are the same. Whether you are driving this angle to 0 or this y coordinate to 0 will define your final outputs, what those are, and decide what you are going to get. So if you consider now, there are the adder subtractor, 3 adder subtractor for the 3 x, y and z variables here. Shifting is there, and for this z, there is going to be a lookup table where these tan inverse values will be stored, which will be taken depending upon z, will be taken, compare those, added those, and then compare, and the sign will be decided so as to rotate that vector in the positive or the negative direction. As far as xj plus 1 is concerned, is xj, so xj is there, plus or minus depending upon that, sigma j 2 raised to minus j yj. So yj is coming here, depending upon j gets shifted by 2 raised to minus j and gets added here, and depending upon sigma j, you will have rotation of that vector to give xj plus 1. So this sigma j will determine whether it's to be added or subtracted, which is nothing but either the rotation in the clockwise or the anti-clockwise direction. As far as yj plus 1 is concerned, you have yj coming directly, but xj getting shifted by j, getting added here, giving yj plus 1. And as far as zj, the initial value from zj, from the table it is considered, this sigma j, whatever is the value, that sigma j will determine whether to add or subtract. Whatever zj plus 1 you get will be the sign to, this sign basically could be that of sin y as far as vectoring mode is concerned, or the sin z rotation mode is concerned, to give you the further sign of rotation, that is sigma j plus 1. So the sigma j and the whatever after addition you are going to get for z or y depending upon the mode you are using, the further sign, that is the direction of the rotation, the vector rotation will be decided. So this is the basically simple hardware which can be easily implemented in FPGA to get you the chordic algorithm implementation. bit serial architecture where instead of adder we have we can work with 32-bit serial. That's bitwise. The streaming of the bits will be done on the adder here, and here also this is your xi getting shifted coming to yi. So xi y1 plus, that is yn plus 1 is yn getting added with xn plus 1. The same thing, LUT here and Zn has been using bit serial architecture. You can again implement that. Word serial architecture, the same thing. You will work with 8-bit words or 16-bit, or it could be pipeline implementation for, increasing the sample rate. Hardware architectures which can go for implementation. Now, this accuracy of this method, basically, if you do and if your angle is limited from -90 to 90, because the is that we limit it to 0 to 90 so that any other it is a say 120 is 90 plus 30 or sine of minus 30. So you can get from all the trigonometric functions in the first quadrant the functions also. So we are limiting it to maybe -90 to 90, and if the iterations, then the accuracy is within 1/2 raised to 2. It means, suppose if I take 20 rotations, because you have just seen after 14 rotations, it has got converged to a value of 40 degree. 20 rotations, if I do it, this will be of the accuracy will be of the order of 1/2 raised to 20, which will be within 10 ppm. So the accuracy is very good. It is much faster within finite few iterations. You can get the vector to converge. You can get the algorithm to. These are the depending upon what the final values of different coordinate systems depending upon the mode. You can target for cos sine theta. The final value is 0. Here rotation mode we have seen. As far as the vectoring mode is concerned, you get a value of under root of x square minus y square. Here y is forced to 0, so yf will be 0, and here it will be except upon yf, that is tan inverse of theta you will get. In the hyperbolic, similarly, cos theta, sin theta, z is reduced to, driven to 0. In the vectoring mode, similar to x square minus y square under root, but here it will be hyperbolic tan inverse theta. In the linear mode, in the rotation, you get a value, final value will be x, xf equal to x, yf is equal to y plus x theta, driving z to 0, so this will be 0. In the vectoring mode, it is x, y will be 0, z plus y by x, and so on. And particular thing, you can see that depending upon the initial values and the functions as such, whether it is a rotation or the vectoring mode, you can get natural log, you can get trigonometric, you get exponential functions, sine, hyperbolic, normal, rectangular. All these are values possible if you try to select the mode, select the initial values, and decide which type of system you are working with. It's a linear or it is a hyperbolic coordinate system. So coming to an end, I'll say evaluation of rotational functions is more efficiently done than the Mach units. No Mach unit was coming into picture, and hence it saves a lot of hardware cost. It implements both parallel and pipeline architectures. So both structures are there. That is, we are going through a pipeline, also putting delay elements in between, and also because you are working on X, Y, and Z in parallel. The regularity is there because once you develop an adder, the adder same can be used there. Once you develop a barrel shifter, the same can be used. So modularity, regularity is there. And it's a very good, you can also implement an VLSI array processor. The utility of the Cordic-based architecture lies in its generality and flexibility. Can be successfully implemented in FPGAs, and that is why the importance to the Cordic processor, because we can do it, we can see, we can implement many DSP related operations, computations, and convergence is within finite number of operations with accuracy for n is equal to 20. You can compute it with within 10 ppm. It is an iterative algorithm. We know a systematically iterating by choice of proper angles. Adds or subtract and shift operations are there. Scaling can be adjusted to the gain of processor, that is the initial value, as we have said. So you try to eliminate that. Two more, three coordinate systems and applications we for solving linear system of algebraic equations, for filtering purpose, for DSP computations, image video processing, three-dimensional graphics, all that. So through this delivery, I summarize it that we have seen what are the various computations in digital signal processing, how VLSI technology comes as a boon to implement those, what are the popular DSP architectures, which will either give you area optimization or will you speed enhancement or can be performance-wise better or reduce the power. I mean, there are the algorithmic approach which I could not touch because it's impossible for me to touch all those and work out those. But I think you can refer those maybe from the literature or Keshav Parikh's book. A standard book is there which he also has, invented many of these architectures. Chordic algorithm I had just taken as an example how it can. How nice architecture it is, and without going from back in it, how you can implement those using only adder and shifter. And in the various modes and coordinate systems, we can have the various difficult numerical computations being done very easily and a very good candidate for VLSI implementation. And in our labs, we can do it using FPGAs. Information communication era as such, what we want is everything needs to be in digital and high-speed era. No doubt, this is analog mixed signal, but I think analog signal after discretization, as I had shown in the initial slide, that we had to sample it using, quantization. Initially, you have to do the sampling, then you have to do the ADCs and discretization, and then the samples will be taken for digital signal processing. So a part of that, you can say an extension of your all the three STTPs has been done here through giving emphasis more on DSP and algorithms and architectures. So one has to understand what the VLSI technology is there, and and for which FPGA which is available today, open source, is because of its many advantages. You can try to see that those algorithms and do some 40 iterations and see, yes, really whatever the at our fingertips. We can do it at whatever place we are, and we can do many, what I say, the local problems we can try to solve using such type of easier and low-level implementations and can benefit the society. Our students can become entrepreneurs because they already have the knowledge of all logical design, analog designs. They can try to implement those for the solving their local problems and try to give the solutions. And they themselves, instead of seeking the jobs, they will give the jobs. They will become the job givers and will make many, what I can say, young generation to make our Bharat as Atmanirbhar. So what I do, you
हॅलो मॅडम. मॅडम सडनली आवाज हे झाला, ब्रेक होतो. Ma'am, Shaila ma'am, your voice is breaking just now. तुमचा व्हॉइस ब्रेक होतोय मॅडम. हॅलो. हॅलो मॅडम, जस्ट केला, जस्ट आता तुम्ही आत्मनिर्भर बोलल्यावरती आत्मनिर्भर निघून गेलं. Yes, yeah, you are not आत्मनिर्भर now, that's why it happened. नाही पण नाही, आता तुम्ही तुमचा आवाज केलाय, तुम्हाला आम्हाला काहीच म्हणायचं ना, तुम्ही परत लॉगिन करताय काय करताय? हा, आणि आता एक काम करा, तुम्ही शेअर नका करू साईड संपली. आता मी माझे काही क्वेश्चन असेल कोणाचे घेऊन काढत नाही, आमच्या साईडने शेअर करतो, शेअरिंग करून टाकतो. हा मी लॉगिन करून करा. Madam will join for 2 minutes. This way. Let her say thanks for this. Just 2 minutes. Achha, in between, let me give you some instructions for tomorrow. So good. This third STTP is also over, almost over, not over because one session is pending. So we had shifted session by Dr. Prashant Nair to tomorrow 10 o'clock. So please join that session at 10 o'clock. Before that, you appear for the quiz. Be prepared for the quiz. You have to read, you have to go through the videos. I hope you will do that. Last exam hai, final exam hai. So you do that. And 1 hour examination, 60 marks, objective type. Again, starting time 8. I have kept purposely up to 11. But if you appear between 8 and 10 and finish off, it will be good. Because then Prashant will be there with us from 10 to around 12. I have given him a slot 10 to 12. So whatever time he wants to speak, let him speak. But he will be joining at 10 a.m. So please join for 10 a.m. And then 2 p.m. please join, because we have a very good person with us for the validity session. So we will have his speech at 2 p.m. on mind power. And I have already shared his profile, brief profile with you on WhatsApp. Mr. Jagdish Singh, he is the mental trainer for so many teams, including Mumbai cricket team, to boxing team, to tennis team, to athletics, to Olympic team, and so many. And he's an official mental trainer from the Sports Authority of India. So I think it's a good opportunity to talk to him. It will be good that if you join at 2 p.m. That will be nice. I think Shaila madam has come. Shaila ma'am, मॅडम तुम्ही ऐकू तरी शकता का आम्ही बोलतोय ते? स्नेहा मॅम.
येस सर, आय एम हिअर सर.
शेअर करा मॅडम. अच्छा, मॅडमचा आवाज येतच नाही.
हा, मॅमचा आवाज
मॅडम
येतो.
तुम्हाला माझा आवाज येतो का?
तुमचा आवाज येतोय ना सर?
मी अनम्यूट झाले. हॅलो सर. हॅलो.
येस मॅडम.
Now the connection is there. ज्या अकॅडमी मध्ये मी आता येते ना, त्यांचं काही 2 तासाचं दिसतंय असं मला वाटतंय.
अच्छा, ओके ओके.
असं काहीतरी होतंय, कारण बरोबर 2 तासांनी anyway, I think I can take the questions if they have.
If anybody has any questions before I say thanks to ma'am, anyone has any questions? Madam, I don't think so. मला वाटतं काही प्रश्न नाहीयेत. मॅम, थँक यू व्हेरी मच. आय अप्रिशिएट युअर मोटिवेशन and your passion and your zeal for the academics, it's unparalleled. It's simply unparalleled. Thank you very much. You are sitting at such a remote location, I know, and under what circumstances you are there. What are the issues that you are handling? That also it's a salute to you, ma'am. And still, you kept your promise, and that you are going to deliver. It's really exciting.
Yeah.
You are a role model for many of us, and I think we should follow this passion. That whatever is the promise given, you have to fulfill, and that's what you have done today, actually, ma'am.
Yeah, I mean, with some problems, I could do. Initial hurdle was there. Again, in the last, there was a hurdle. Anyway, but I think what I can do is that the PDF copy of my presentation, I will just Moodle. I can access that.
Yes, yes. Yes, you can send it to ma'am. I'll put it on Moodle. And please accept. Yeah, you send it to madam. I will put that PDF on Moodle. I'll put your copy of your presentation on the Moodle platform. Okay, ma'am.
Okay. Thank you,
And
sir,
kindly
for
accept
giving
this
me
virtual
opportunity.
memento from us certificate.
Of this so that I can have it in
Okay. Thank you, madam.
the meeting. Thank you. झाली का लीव झाली का
Okay, madam. Thank you. Thank you, madam. Thank you. Thank you. Thank you, madam. Thanks a lot. Thanks a lot. So, thank you, everyone. Thanks a lot. We are done over. Tomorrow we'll meet 10 a.m.
राठोड सर
हाँ बोलो साहब.